Okay, so now C is the curve that is the boundary of the semicircular region. This semicircular region with counterclockwise orientation. Okay, so what does the picture of this region look like? Something like this. That should have been a top of a circle. Let me do a better job. Okay, and it's going to be radius 4. So the top half of a circle of radius 4, and we're doing the line integral around the boundary of it. So it's something like this. And we want the counterclockwise orientation. Okay, so this is a Green's theorem problem. So we want to compute this integral, and we're going to use Green's theorem to compute it as a double integral. Okay, so notice that q of xy, let's do p first. P of xy, that's the function that is multiplied by dx. So p of xy is equal to y cubed. And so this means the partial derivative of p with respect to y. Because if you look at Green's theorem, you want the partial derivative of p with respect to y. The partial derivative of p with respect to y is 3y squared. Q of xy, that's the function that multiplies dy. Q of xy is minus x cubed. And so this tells us the partial derivative of q with respect to x is equal to minus 3x squared. Okay, so it means the integral then, let's call this region R. The line integral is going to be the integral over the region R of px or qx minus py. So q sub x is minus 3x squared minus p sub y. So that's going to be minus 3y squared dA, or this is equal to minus 3 times the integral over r of x squared plus y squared dA. And we are integrating over a semicircle, so this is a perfect polar coordinates problem. So this is minus 3 times the integral. We'll do theta on the outside. And now theta is going to go from 0 to pi because we just want the top half of this circle. And then r is going to go from 0 to 4. And we'll write the r dr d theta. And then x squared plus y squared is r squared. Okay, and now this is an integral that you can do on your own.